And here they all are. See, the control parameter R goes from 0 on this end of the rectangle to 4 on this end of the rectangle, and for each intermediate value of R, the attractive set is indicated in red. So we draw a vertical line here over some value of R, and where it intersects the red locus, it shows that we have an attractor in that location. This domain is parameterized from 0 to 1. And after we get through larger and larger values of R until we get up to around 3, then we see that this fixed point divides into the two periodic attractor. And then as R continues to increase, we get this other point where there are 4 red points over this particular value of R, because there's a 4 periodic attractor. And a little higher, there's a 16, a 32, and so on. And then finally we get, you see this solid red interval, that's chaotic behavior. And then there's this black stuff up here, hard to see. We could see it better if we could zoom, if we could take this portion of the, this is called the response diagram, just this 1 inch or so on the right edge of the rectangle, and blow it up so it filled the whole screen. Okay, so we can do that. Let's say I want, let's take this value right here. It goes for R 0, 1, 2, 3, and 4. So let's blow up the part from R equals 3 to R equals 4. We have these sliders to determine the value of R on the left and the right edge of the rectangle. So I'm going to change this minimum to 3. Can you see those little numbers? Probably not. I changed it to 3. And this one I'm going to leave 4. That's the right hand edge. And then I'm going to make it again. So see, now it's been blown up. So here we have R equals 3, and here's R equals 4, and what used to be just a quarter of the screen now fills the entire rectangle. And here we see that 3 is shortly after the bifurcation where the fixed point changes into the 2 periodic attractor. And here we have the 4 periodic attractor, and then there's 8, 6, and it goes rather rapidly. And look up here, this black line that previously looked like this one has been stretched out wider, and we can see within it there's 1, 2, 3 points in the attractor over that particular value of R. And that's called the 3 periodic window. Chaotic behavior disappears and periodic behavior reappears, and that keeps on happening. So let's see, that's 3, 3.5, 3 3/4. Let's change this to 3 3/4 and do one more zoom, and then I'll stop. So there's a very narrow strip I'm going to blow up. And here I missed the 3 periodic window, which is off to the right here, sorry. But look what we've got here, 1, 2, 3, 4, 5. There's a 5 periodic window in there. Okay, so this is your assignment, is to figure out what this means. And there are some suggestions here, and there are also various books. Some of you who are math teachers might like to look into this further, and there are several books that are just about this one system. But I would like to move on to other systems to avoid thinking that all dynamical systems look like this. But this is the basic idea. Dynamical system, you have basins, attractors, and separatrices. What kind of attractors? There are 3 different kinds: point, periodic, and chaotic attractor. What's interesting is about the dynamical system is when it has a control. So it's a dynamical scheme, and then changing the control produces bifurcations. Three kinds of bifurcations: catastrophic, subtle, and explosive. All of the bifurcations we're seeing in this response diagram are subtle bifurcations.